This conference will now be recorded.
So today we'll be learning about nuclear forces and radioactivity. So we have seen that the dimension of nucleus is very tiny, right? And we have learned what is the composition of nucleus also. So we have seen that in the nucleus you have neutron, okay, and proton. So this has no charge. Here no charge, and here you have positive charges. This is proton, right? And see when this if you see the nucleus, it has a radius we have seen of the order of some femtometer. Femtometer means nearly 10 to the power 15 meter. So this is the dimension. It is very tiny dimension. So to keep holding these neutron and proton together at a very tiny space, you must be requiring a very strong force, right? Very strong force. Now there is a very important question: what type of this force is? What is the type of nuclear force, and what are the characteristics of nuclear forces? So now look, you have nucleus, protons, right? Protons, and they repel each other according to Coulomb's law. If I say nuclear force is attractive force, just like Coulombic attraction, then it is wrong. Why? Because inside a nucleus you have neutron which are neutral, and you have protons. See, these protons are repelling each other. That means the electrostatic repulsion or Coulombic repulsion is already there between each other. So Coulombic repulsion means electrostatic repulsion, all right. And see, you need some force which is actually very stronger, much more stronger to overcome this repulsive force, isn't it? So you require a force stronger than Coulombic force, right? Coulombic force. Now you may think that why not gravitational force? The nuclear force is neither similar to Coulombic force nor it is similar to the radioactive gravitational force, because the Coulombic force is almost 10 to the power 40 times greater than, see, if I say Coulombic force or electrostatic force, it is 40 times greater than Fg, gravitational force. So gravitational force is very weak force, and it is not possible for gravitational force, neither for gravitational force or electrostatic force, to hold nucleons. That means neutron and proton at a very tiny compact space. So for that you must need a very strong force, very strong force. So that's why nuclear force is a strong attractive force that binds the nucleons together inside a tiny nucleus. So it is a very strong force. So nuclear force is called a strong force. Okay, electrostatic force is known as electromagnetic force or electrostatic force also. You can electric force also, you can say electric force. So there are actually four fundamental forces. Four fundamental forces you might have read in the 11th standard. There are electromagnetic force, gravitational force, weak force, and strong force. So these strong forces are actually nuclear forces are the strong forces. Why? You have protons. These are charged particles. They repel each other. So your force has to be strong enough to overcome this repulsion. Okay, and this force you'll see in very short time. I'll discuss that nuclear force is actually having properties certain properties. They are not like other forces. Let us let us learn the properties. See, we have seen that the nuclear force has to be the strongest force. So it is the strongest interaction. That means this neutron neutron and proton, this force acts between neutron and proton, proton neutron, sorry, proton proton, neutron neutron, and these forces are very strong. That's why they are actually inside the tiny nucleus. Now it is a short range force. It is a short range force. So what does this mean? Short range force means this force this force acts in a very tiny region. Okay, it acts actually between its nearest neighbor. It is a short range force. Okay, so as you see, the force nuclear force is acting inside a single nucleus. Okay, single nucleus. So the range is of some femtometer order. We'll see we'll see from this graph when this we'll discuss that nuclear force. See, look this graph now itself. This is the potential energy for two nucleons. Okay, two nucleons when they are uh, when they are some distance apart. Suppose this is the r distance apart. If we increase or decrease the distance between these two nucleons, then we'll look that depending on this r, the force is becoming the nuclear force is becoming either repulsive or strongly attractive force. Look this force here. This is actually potential curve, and this potential is becoming very like it is becoming minimum around some zero point 0.8 femtometer. Around some zero point 0.8 femtometer, the potential energy is becoming minimum. Now you look, if you go away from this R0 or below R0, what we are seeing that the potential energy becoming negative. See here it is negative when R is greater than R0. Greater than R0. After the minimum value, this is remaining negative itself as you increase the distance between them. But if you decrease the distance, if somehow your distance becoming less than R0, then the potential becoming positive. Look here, potential energy becoming positive. That means it is repulsive force. Repulsive. So the nuclear forces between the two nucleons will be repulsive if you bring two nucleus at a distance lesser than R0. That means it is lesser than 0.8 femtometer. Okay, so So this is the case, and this force is so nuclear force is very short range force. That means it will interact with its nearest neighbor itself. It doesn't interact with, or it is not acting between next nearest neighbor or far neighbor. Okay, all right. So this is called short range nature of the nuclear force. Now we'll see charge independent. The nuclear force between a proton and another proton, then a proton and a neutron, okay, neutron, or a neutron with another like between another neutron. So the nuclear force, F in nuclear force for all of them will be the same. So it is charge dependent force. Sorry, independent force. Nuclear force is charge independent force. It is the same force which is acting between the neutrons or neutron and proton, or between proton and proton. Okay, same force it is acting between proton and neutron and neutron. Okay, neutron or proton has the same nuclear force. So that's why it is charge independent. Charge independent. That's why neutron is also is in compact or neutron is also very tightly bound inside the nucleus. If it would have been an electric force or electrostatic force or electromagnetic force, then neutron would have not been tightly bound inside the nucleus. Okay, so we have got up to here charge independent. Now it has a saturation effect. As I said, saturation effect means nucleus. See, nucleon is in the nucleus. Nucleon in the nucleus will interact with the nearest neighbor only, and it remains unaffected by the presence of any other surrounding nucleus. What does this mean? Suppose you have proton, neutron, proton, neutron, like that you have. If you increase the size, see, the nuclear forces act between these only, but if you bring another neighbor, they may not they may not experience nuclear forces. Okay, so this effect is called saturation effect, when the nuclear force is actually inactive for the further nucleons. So I'll just try to make you sure what is saturation effect. You have nucleons, you have another set of nucleons here, another maybe here. So you look, the nuclear force will be saturated by this inner atom itself. If we just consider in terms of cell theory, okay, cell model, then nucleus has inner layer. So nuclear force will be always confined in the inner layer. It doesn't go out of the inner layer. Sorry, inner layer. Yes, and that is why they are. See, nucleus is not affected by the presence of the other nucleus. Okay, because for each of them, the force nuclear force is very short range. Okay, and the nuclear force gets saturated. Okay, fine. Then the nuclear force is spin dependent. That means, see, we will see for an electron or for a proton or for a neutron, every particle they have their intrinsic spin quantum number that you have learnt in your chemistry. Spin quantum number or magnetic quantum number. So that is denoted by some arrow like this. Okay, this is the spin. Okay, now this nuclear force is actually said to be dependent of this spin, dependent on the spin. So if there are two spins, like which are oriented like this. So there are two nucleons. If their spins are oriented in a particular orientation, then only they will interact with each other. Otherwise, not. So in case of deuteron formation out of proton and neutron, it is seen that when the spin of both proton and neutron are in the parallel direction, suppose this is neutron, this is proton, the spins are in the parallel direction, then only the deuteron formation happens. Okay, all right. And this force is not a central force. Central force means what? We know there are two central force we have already learned. One is gravitational force, another one is electrostatic force. So central force always acts along the line joining the two charges or two masses or whatever. Okay, in case of gravitation, it is acting along the line joining the center of the two masses. Okay, so this is called central force. Central force will be always directed towards or away from the direction. Okay, so central force means the force which is always directed towards some point or away from some point, or in other words, central force does not act along the line joining the two nuclei. That particular force is called, so that's why this nuclear force is called central in nature, sorry, non-central in nature. Non-central in nature. Non-central means they don't have hard and fast rule to act along the line joining the two nucleons. And exchange force. So this force is actually arising. This strong nuclear force arising, strong nuclear force arises due to the exchange of pi meson between the nucleons. Exchange of the pi meson. So there are three types of pi meson. One is pi plus, pi 0, and pi negative. So these are the things you will be learning in your higher standard also. So I'm not going into that detail. So strong forces are actually generated or produced. Strong nuclear forces are produced due to the exchange of pi meson between the nucleons. So that's why it is called exchange force. Now we'll go to another topic called radioactivity. So this radioactivity is a phenomenon in which an unstable nucleus undergoes a decay. Unstable nucleus undergoes a decay, and it is actually a spontaneous process. It is a spontaneous decay, spontaneous phenomenon, spontaneous or spontaneous decay. That is called radioactivity. So radioactivity is a nuclear phenomenon in which an unstable nucleus undergoes a decay, and this decay is actually spontaneous decay. And see, this radioactivity was first discovered by A.H. Becquerel in 1896. And this discovery, if you read the textbook, you will see this was very accidental discovery. What he had done, he actually was uh, doing various spectroscopic experiment with phosphorus and fluorescent materials, and in the process of experiment, what he had done, he had kept on uranium, potassium sulfate, potassium sulfate wrapped with something, a black paper, wrapped with a black paper. See, upon illuminating with some light, this particular chemical, uranium potassium sulfate, this particular chemical was wrapped with a black paper, wrapped in a black paper, and then this was kept separated from the photographic plate, PP, photographic plate, by keeping a silver plate in between the plate and this black cover. So there was a black cover where this material was there, black cover, then a silver piece of silver, and then photographic plate was kept. Photographic plate was kept. So this arrangement kept for several hours. This is a black wrapping with irradiated uranium potassium sulfate. Then what Becquerel noticed that this photographic plate become become black. That means what? Photographic plate has been plated, or photographic plate has been developed. Okay. So from here, Becquerel guessed that there must be there must be a ray which is, or a light which is reaching to the photographic plate, even penetrating the silver and the black wrapper, and silver plate is being penetrated by the ray which are which are produced from this uranium potassium sulfate radioactive material, and penetrating, and it is developing the photographic plate itself. Okay. So this is the accidental discovery of radioactivity, and as we know, radioactivity is a nuclear phenomena, and it is spontaneous decay of some unstable nucleus. Now we have to see that there are different types of radioactive decay that occurs in nature. There are three types mainly. One is alpha decay. So there are three types of decay happens in the nature. This is natural radioactivity. The decay. That means what? Suppose you have a nucleus, a nucleus, radioactive nucleus ZA. Then alpha decay happens, means suppose this is radioactive. So alpha decay happens. Alpha is actually a nucleus of helium. Alpha decay means a nucleus of helium is getting released from this particular radioactive material or nucleus, radioactive nucleus. So then after, see, since it is having this alpha particle is having 4 times of the mass and 2 times of the, like, proton numbers 2 and mass number 4, so the residual nucleus or the daughter nucleus will be A minus 4. Okay. And this will be, the proton number will be reduced by 2. So this is the daughter nuclei. This is called daughter nuclei, and along with alpha particle. Daughter nuclei. Okay, all right. So you have understood that alpha particle decay means it is the helium nucleus which is getting released from a nucleus. Then beta decay. What is beta decay? Beta decay, in beta decay, either electron can emit from the nucleus or positron. Positron and electrons are coming out from the nucleus. So what is electron, that you know? It has negative charge, is equal to 1.6 into 10 to the power minus 19 coulomb. And then positron, actually it has same mass as the electron, same mass as the electron has, and also it has positive charge as that of electron. All right. So positron and electron decay is called beta decay. Sometime positron decay will happen, sometime electron decay will happen. If there is electron decay, suppose I have nucleus, this one, Z minus 2. Okay, now for this, if again beta positive, that means positron decay happens. Positron decay happens, then what will happen? So positron decay means positive charge has been again reduced. So it will be here Z minus 3, and mass, it has a very negligible mass, so mass we don't see the mass to be changing. Okay, so A minus 4 remains the same. Here you look, Z minus 3, it becomes Z minus 3. Okay, because positron is going out, means one positive charge is going out. Now it will happen opposite. If you take one electron away or just release it, so you'll get here positive, see, negative electron has gone, so positive charge will be increased by 1. Okay, so this will be Z minus 2 again. All right, I hope we'll discuss these things again. And gamma decay, so there are 3 decays, 3 process of radioactive decay. One is alpha decay, then beta decay. Okay, beta decays, and then this is beta decays, and then gamma decay. When a radioactive nuclei disintegrate into its daughter and other entities, the daughter nuclei still have certain energy which doesn't allow the nucleus to be in the ground state. So that's why the excess energy of the daughter nuclei will be released as gamma photon, and the daughter nuclei will come to a ground state. Okay, this is about gamma decay. All right, now we'll see there is a law of radioactive decay. That means radioactive materials will follow a particular law while this while decaying spontaneously. For any radioactive sample undergoing alpha, beta or gamma decay, it is found that a number of nuclei undergoing decay per unit time is proportional to the total number of the nuclei present in the sample at that time. I'll write this. Okay. So what is found? It is found that the number of nuclei undergoing decay per unit time is proportional to the total number of nuclei present at the beginning. Okay. Suppose n be the number of nuclei present at any time t0. Okay. Or say at any time it has t, sorry, n. Okay, any time n be the number of the nuclei present. Like, see, we are just trying to find out the radioactive law, decay law. So in the beginning, suppose the total number of nuclei in some substance, radioactive substance, is this n, and after or during in during delta t interval of time dn nuclei undergoes a decay. Then the decay rate can be written as, see, delta n by delta t. This is the decay rate. This is the number of nuclei which undergoes disintegration during the time interval delta t. So this is directly proportional to the number of nuclei present in the beginning. Okay, this is the fundamental rule which actually radioactive nuclei follow during the decay. So look, if I write in terms of equation, there will be a disintegration constant, which, like, there will be proportionality constant which is written as lambda, and this is n. So this lambda is called disintegration constant or decay constant. Disintegration constant. Okay, disintegration constant. Now look, one more thing, you see delta n. So this is actually a negative quantity with respect to time. Okay, this is a negative quantity because, or I'll say the change in the number of nuclei will be a negative quantity. Dn is equal to this because this is getting decayed. Okay, and see, if we take this time interval this to be very tiny or tending to zero, then this particular equation can be written in terms of derivative dn by dt with a minus sign over here. It is equal to lambda into n. I'll write down here. So look, this is dn dt is equal to minus lambda into n. Now if we integrate this term between the time interval some t0 or t is equal to, directly let us take t is equal to 0 to t, and this at t is equal to 0, that is before we observing the decay, the number of nuclei in the beginning was n0, and now after certain time t, suppose there would be n. We have to find out what is this number n at after any time interval. Okay, so if we integrate it, look, this part will give you a ln n by n0, and this would give you lambda into t. Okay, so this integration gives you ln n by n0 is equal to minus lambda t. Okay, so now what we'll do, we'll simplify this equation further. So ln n by n0 is equal to minus lambda into t. This can be written as n by n0 e to the power minus of lambda into t. Okay, so you can even write this as n is equal to n0 lambda e to the power minus lambda t. So this is actually called the law of radioactive decay. This particular equation is called law of radioactive decay. Okay, so this is called law of radioactive decay. Radioactive decay. Okay, now see, using this equation you can solve many problems. So there will be, see, this lambda, this is called disintegration constant, sometime it will be given, and you will be given initially how many nuclei were there in a particular radioactive substance, and then you will be asked to find out after 6 months or after 2 years how many nuclei will be present in the sample. So you have to use this decay law, okay, to find out number of nuclei present in any radioactive substance after any time t. Okay, radioactive substances are continuously disintegrating. Nuclei are actually getting disintegrated, and after how many you will get, like after some hours or some years, how many nuclei will be present undecayed in the sample, that you will be able to find out from here. So n0 is the initial number, lambda would be given, that is disintegration constant, t is the time after what you have to calculate the number of nuclei present in the sample. Okay, so this is how there will be numerical problems asked depending on this radioactive decay law, this equation itself. Now we'll see, sometime we are interested in what is the rate of decay rather than how many decayed or how many remaining. We are interested in in rate of decay. Rate of decay. Okay. See, rate of decay is denoted by R. Let me write rate of decay. It is denoted by R, and this R is actually, see, it is the rate of decay, rate of nuclear decay, and it can be expressed like this is the number of nuclear decay per unit time. Okay, so rate of nuclear decay means number of nuclei decay per second. Number of nuclei decay per second. Okay, so this is given by dn minus dn by dt. Okay, now if you put the value of n is equal to n0 into e to the power minus lambda into t, right? This term. Now if we integrate this whole term, n0 is constant, minus lambda comes down, and it will be again e to the power minus lambda t. Okay, so you look, this rate of radioactive decay R can be written in terms of an equation. Radioactive decay is equal to, here minus was there, here minus will be there, so this minus will be getting cancelled, so it is actually lambda n0 e to the power minus lambda into t. So this is the one, which express the decay rate of decay. So this particular multiplication we can write in terms of R0. So look, this follows the similar type of formula or equation. See here, n is equal to n0 into e to the power minus lambda t. So radioactive decay per second actually varies with time. Decay per second varies with time because, see, with time number of initial nucleus that also changes. That's why radioactive decay in radioactive decay the number of undecayed nucleus will be changing. Okay, so the R is not a constant term, it is actually a dynamic term. So rate will change depending on the initial number of initial nucleus. Okay, so this is R is equal to R0 lambda t. So this is also called alternative form of radioactive decay law. Alternating form of alternating alternating form of radioactive decay law or law of radioactive decay. This is so what we have got so far. We have got n is equal to n0 e to the power minus lambda t, and with radioactive rate of decay we have got R is equal to R0 e to the power minus lambda t. So these are actually following similar type or same equation. With R is different for this Like yeah, so this and this are not true, not same. N0 not equal to R0. You should not compare like this. Okay. So these are the two equations we have got. Now see, this can be written. See here it was R when we have seen minus dN by dt. Here was lambda N0 e to the power lambda t. So this is what we had got, and this lambda N0 we have kept written as lambda 0. Now this can be written as lambda into n. This is actually see n0 into the power lambda t. That is the same n. So you can find out radioactivity. So if you know the disintegration constant initially how many were there, then you know the rate of decay. Rate of decay. Okay. So for today I'll stop it here. Next day we'll take a few numerical example on this radioactive decay and all, and at the same time we'll learn two time parameter related to this radioactive decay. One is called half-life, and another one is called average life. So average lifetime and half lifetime. So 1 over lambda is called actually average lifetime, and half lifetime will be given by 0.693 divided by lambda. Okay, this is called half lifetime. T half is equal to 0.693 by lambda. So what is T half? T half is the time when radioactive nuclei undergoes exactly by half. Initially suppose it was n0. Now after time t, if this is t half, then n0, so n becomes n0 by 2. Okay. All right, we will see half life and what are the significance of half life and average lifetime, and then we'll take up numerical example with that. So next day we'll learn about t half, and then this is called half lifetime, and mean lifetime also will be discussing. At the same time we'll discuss alpha, beta decay, etc., and numerical problems also. Okay, so I'll stop it here for today. Deepa, if you have any question you can ask me now.
No, sir.
Okay, if you don't have any question or query, I'll stop it here. We'll discuss again. If you have any doubt as such, you can ask me in the other class also. Okay, bye for today.